Welcome to today's Research Pays Off. I am going to hand it over to our speakers for today, Bora Cetin and John Daniels.
Thank you, Lauren. And thank you all for being here for today's presentation. Do you all see my screen?
Yes, looks great.
Yeah. All right, I'll turn my camera off too, just in case if there are any bandwidth issues with anybody. And today it will, hi everybody, I'm Bora Cetin, a faculty at Michigan State University, and my colleague Dr. Daniels from University of North Carolina at Charlotte. We work on this topic in general almost a decade with Professor Daniels, who has been a great mentor for me as well. So we started on this project using water repellent, engineered water repellency to improve the free storage. We started with free store resistance of soils and pavement foundations, pavement systems, and then also look into the improving using the similar technology on other avenues. And today we specifically talk about improving moisture resistance and control of pavement foundation systems via engineered water repellency. We will switch between me and John throughout the presentation. And we have our PhD students who work on this project on the call too. What's Dr. Nakwi and Emmanuel. Please, Wasif and Emmanuel, feel free to chip in to answer any questions or if anything that we didn't cover during presentation. Dr. Daniels, anything to add?
No, just happy to be here and look forward to sharing some of our work.
Yeah, thank you. And we have a specific project on this topic, and these are the TEP members. We really appreciate their effort and help on going on this ongoing project. But this project, like I said, started almost a decade ago with between me this whole idea of using engineered water repellency in soil systems and pavement systems. With Dr. Daniels, he also have used this for before a decade before, and he was willing to work with me to advance this technology even more before. But this topic has involved many people, many agencies, but recently we really appreciate mnroad and Minnesota DOT's help. We will get to this. We built a test site on mnroad, and it prematurely needed to be prematurely had some performance issues, and especially on the control side, not the one that is treated with our technology. And really, mnroad and Minnesota DOT help a lot for helping us to rebuild these test sites. So we really appreciate their help. Of course, NRRA TEP members, and I will touch bases a little bit on this throughout the presentation with Dr. Daniels too. Iowa Highway Research Board, we have a project with previously, and it's about to come to an end with Iowa Highway Research Board. We applied this technology on the unpaved roads, gravel roads. Again, we appreciate the funding for the National Research Alliance, and the first project that this started with National Science Foundation, so we really appreciate their funding and give us a boost to start this research in the beginning. Then Iowa Highway Research Board followed up with implementation stage of it, and we really appreciate NRRA to provide another funding to try this on a low volume paved roads. And of course, without the team members that we listed on both teams there, and I think Dr. Nakwi did his PhD on this, and he's on the call today, and Emmanuel Adeyanju also, along with other colleagues that we listed here, are on the call here. So again, today's outline is basically talking about what is we have 5 main topics. The first one I'll cover quickly with the impact of moisture on pavement systems, how impactful it is, especially in climate zones like Minnesota area. And then Dr. Daniels will talk about what is water repellency. Then I'll take it over to talk about some laboratory-based research results from our previous research projects. And then Dr. Daniels and I will talk about the current field-based research that we are conducting at mnroad. And then we'll talk about what we will be continuing to do. So the first chapter is impact of moisture on pavement foundations. I assume many people in the call knows that moisture is one of the most challenging problem in geotechnical engineering, and as a result of it in pavement engineering, pavement systems, because while we have asphalt and concrete layer on the surface, we have multiple layers, very thick layers, foundation layers, base, sub-base, and subgrade soil underneath, and moisture has significant impact on their performance, especially if you have climatic zones like Minnesota, where your material or pavement systems will be subjected to significant numbers of freezing and thawing, and that causes significant issue. When that freezing temperature interacts with moisture presence, it causes significant issues to the upper pavement systems. And you can see some of these damages caused by this impact of moisture on the pavement systems. And again, I keep talking about the climate zones, even though National Road Research Alliance has multiple states throughout the country. The research project, this current research project funded, is applicable to the wet freeze zone and even wet non-freeze zones mostly. And we built the test sites in Minnesota, which is the wet freeze zone, especially in that area, geographically also perfect for farming, but those soils are very weak for building roads. And on top of that, you're in a wet freeze zone that is one of the most challenging zones, especially if you have high groundwater table level and high moisture presence within your pavement systems. So so as a result of this wet freeze zone and high moisture presence within your pavement systems, there are several proposed solutions in the past: chemical stabilization, mechanical stabilization, moving and building roads with more granular and permeable materials. However, in the proposed solutions, since over the last decade, we have been advocating for and trying to understand is to use engineered water repellency. But first, before we get to this, what are the three basic requirements for frost action? The first one is you need a freezing temperature below 0 Celsius degree, and water availability, moisture presence, and frost susceptible soil. Like I said, especially wet freeze zone, especially in Minnesota, you have freezing temperatures, high groundwater table levels, and frost susceptible soils. In this particular research project and research DIM that we have been working, freezing temperatures, we can't really control that, especially in pavement systems, and frost susceptible soil can be very costly. You can do this locally, but removing miles of frost susceptible soil can be very costly. So what we try to do, we try to manage the water availability. We try to create a hydraulic barrier by using engineered water repellency to minimize these frost action within pavement systems. And Dr. Daniels, you want to take it from here?
Yeah. Please call me John, and thank you, Dr. Cetin. And so we'll work together to move through this swiftly. And as you can see, water repellency is all about preventing water from entering into our soil. And look, this is, as Dr. Cetin has mentioned, as Bora has mentioned, this is an area that I've been working on for almost 20 years. And frankly, I think I would study it even if it had no useful application, because I just find it fascinating. I do believe there are applications because, again, water has such a profound impact on soil behavior. And so if we can control where water goes and where it doesn't, we can have an impact. So if we look, for example, the next slide, you'll see, what is the mechanism? Well, of course, this occurs naturally. And a lot of times you think of this as being a problem naturally in terms of the soil science. And so that's where a lot of the literature has formed. And so the picture on, I guess it would be the middle of the slide there, you kind of see, um, if you can look carefully, there's a small picture where they're showing sand that's untreated. That's sort of on the left. Yep, Bora's got his cursor on. Then if you go to the right, you'll see after it's treated, you see water beads up. And really, that's what we're trying to do, is come up with the designs that relate to density, that relate to soil type, so we can actually engineer and work with this material. So it's very hard to see on this figure. I know it's a busy figure. If you look to the far right, you see that graph exactly where the cursor is. You see a plot of water entry pressure. That's how much head is required to force water through soil versus contact angle. That's the beating effect that you see of a water droplet on top of soil. And what you notice, if you just kind of focus on that solid line that goes from the lower left to the upper right, what you find is as you increase the contact angle, you transform the soil from one where water is sucked in from capillary attraction in that lower left quadrant. And then when you move to the upper right quadrant, you've got a contact angle greater than 90 degrees. Not only does water not get pulled in from capillary action, but it requires a positive pressure to force water in. And that's what we're trying to leverage with water repellency. The bottom figure there just shows all these potential applications, everything from slope mitigation of erosion, flood defenses, embankments, foundations. There's a lot of things for which this can be helpful. For us and for today, we're really looking at mitigating frost action. So to that end, try to break this down a little bit. The upper left there says FSS. That's a frost susceptible soil. So take a soil that's frost susceptible, treat it with an organosilane, which is a class of chemicals which prevents water from entering. We form a bond, a covalent bond, silicon, oxygen, silicon bond. Most soils have silica within them, and that's really what we're leveraging. And so we go on and we treat it, and we do some relationships between what's the contact angle, what's the breakthrough pressure, what are the soil types, so on and so forth. And then we can go to the field and try this out at a specific site. So that lower right figure is important in the sense that, you know, when Bora is talking about improvement of pavement systems, in this particular case, we're presuming that the drainage features and drainage conditions of a site are working as designed. And therefore, our major concern for frost action is water from below. It's the capillary draw that occurs where your frost penetration occurs in proximity with the availability of groundwater. So that's why you see EWR, engineered water repellency, and we're endeavoring to prevent water, moisture from migrating from a capillary fringe, from the groundwater table, upward toward the pavement. That's the specific problem we're trying to solve. So there's all kinds of considerations, just like any product, right? I mean, what's its safety? What's its effectiveness? How much does it cost? Other considerations in terms of DOT familiarity and awareness of the product. All of these come into consideration, and certainly we've endeavored to blend these things and integrate these things into the products that we've explored here. So these are just some. I've mentioned this before. We really are agnostic to the manufacturer. We've worked with all these companies, but none of them are funding the research. And so really the work that Bora and I have done together is intended to think about organosilanes or think about water repellency almost in a similar vein as lime or cement or even geosynthetics, in the sense that there's different manufacturers of those products. And that's not really our interest in promoting a given manufacturer. It's more, how do you design with this? What are generalizable soil properties? And how does it change when you make it water repellency? And can you design on the basis of those changes from a performance-based perspective? But nevertheless, it is helpful to work with off-the-shelf chemicals to try to make this stuff commercially available and achievable.
All
So I
right.
think this is you.
Yeah, thank you, John. Now, next few slides, 10 or so slides, we will talk about laboratory-based research. We plan to do some laboratory-based research on the current project funded by NRRA, but we've done extensive research the last 8 years on other funded projects by National Science Foundation and Iowa Highway Research Board. So we'll cover those materials And we have collected, this map kind of shows the subgrade materials collected and tested. And we collected 4 from Iowa, 2 from North Carolina, 1 from New Hampshire, and 2 from Alaska. I wish we had collected from Hawaii. I don't know why Star moved down there, but 2 soils from Alaska. And I will talk about some of these research results on some of the results that we did on these some of the selected soil samples here. Again, in the next few slides, I'll talk about results, properties of the soils and results of engineered water repellency that we applied on these soils collected. So we work with one of actually Dr. Nakvis, who's on the call on his PhD dissertation. We work on an Alaska soil from Fairbanks. Here are the result, some information on those soils. Iowa soil from Pottawatomie County, and New Hampshire soil from Hanover, and North Carolina soil from Asheville. And this table, I know a lot of information there that shows the index properties of the soils. One thing that you can see that we look into the thermal conductivities, measured their specific heat capacities and thermal diffusivities on some of these soil samples. And one thing that I wanted to focus on, in addition to, you'll see in the next animation that I have there with the gradation, the soils are...
Payday.
Any questions, or we're good? Okay. So we, as you can see, the soil type that we did both for USCS and AASHTO classification, they are low quality soils, so subgrade soils as expected. And you can see especially the Pottawatomie County and Alaska Fairbanks, they are very predominantly fines. They have predominantly fines content, and their silt content is relatively very high too, especially if you look at the Alaska Fairbanks and Iowa Pottawatomie County soils. And here are the gradations showing that, yes, these are very likely to be frost susceptible soils with that amount of fine soils. And this is the Army chart that is one of the main chart that has been used to determine and classify whether your soil is frost susceptible or not. And based on this graph and based on their percentage by weight finer than 20 micrometer, Alaska Fairbanks is rated as F4, then the other 3 soil are F3, indicating that they are very, F4 is the most frost susceptible, and F3 is highly frost susceptible soils, as you can see. So we really did we got the soils that we wanted to test for. And as an organosilane materials, we have collected, there were a bunch of materials, but we chose to go with the Terrasil, Zydex1, and Zymeter OSF 077 siliconate from Dow Chemicals. These are the Terrasil, have the Terrasil OS1 organosilane 1. Terrasil 1 we labeled as organosilane 1, and Zymeter OFS we labeled as, we name it as OS2 organosilane 2. Terrasil had darker color, and Zymeter had, it's kind of colorless, transparent chemical. And how we determine first whether the soil became hydrophobic and the chemical that we added to soil makes it hydrophobic or not. There are 2 ways. One way to look at it is running a water drop penetration test. This is very crucial, and these are fast tests, so you can really try to have a good understanding of what should be the concentration of the organosilane that you need to add to that particular soil to come up with a right concentration, so you can understand whether you achieve the water repellency. And here are the table kind of summarizes based on the time range, whether the soil has become repellent or not, and if the time range when you drop that water droplet on top of your soil sample that is treated or untreated. If it is not going through more than 3,600 seconds, or if it is extremely water repellent, and if it is strongly and water severely repellent range, it's from 60 seconds to 3,600 seconds. So we treated our soils with 0.1% organosilane ratio, 1% by volume, 1% and 1% and 10%. These organosilane ranges may change depending on these organosilane ratios may change depending on the type of the material that you use, because the amount of organosilane chemical itself that are being used in these chemicals can change from product to product, from model or from brand of a type of a product to product. So if you have less organosilane in certain chemical, you may need to add more of that material. And in addition to the water penetration test, we look into the contact angle, and just like Dr. Daniels mentioned a little bit, to assume that a soil is hydrophobic, when you drop that water droplet on that treated soil, the contact angle that you measure has to be higher than 90 degrees. And as you can see, all the soils that were tested here, even 1 to 100, 1 to 50, and 1 to 10 ratios, organosilane to soil ratios, even 1 to 100 kind of achieve that the soils are hydrophobic, and because contact angle is higher than 90 degree. And unfortunately, the video doesn't play, but we had a video here that would show you pour the water on it, and it just doesn't infiltrate if the soil is treated. And another test that we have run comprehensively last 8 years for multiple different projects, we run the standard frost heave thaw settlement test. This is a schematic diagram of our test setup where you prepare your sample in 6 inches in diameter and 8 inches in height, and you put thermocouples on every inch on your soil specimen, and then you have your based plates on the bottom, and then you have the heat exchangers, cold heat exchanger and warm heat exchanger, to kind of determine that or arrange and apply the whatever thermal gradient that you want to apply and simulate. And you have the myriad water supply that provides the groundwater table level source. And just like John mentioned, we develop this and evaluate this technology against the groundwater table level rises. And then we measure the deformation through laser displacement transducers on each specimen. This is we are able to fit 4 specimens at a time, so we can run the test in 4 specimens at a time. And here is a picture of the test setup that we have been running. And this is outside picture, and we have 2 chiller units, one of them for the top plates and the other one is for the bottom plates. Again, we keep the bottom plate. I'll show you the thermal gradient, temperature gradient that we apply. We run these tests for 120 hours, and the blue lines here showing the temperature, heat and temperature range that we apply on the top plates on these specimens, and orange lines showing the temperature range that we kept at the bottom plate. As you can see, we try to keep the bottom plate warmer, 4 degrees Celsius to sometimes 0 degrees Celsius, but we try to keep it warmer as the soil is supposed to start freezing from the top. So the top plate temperature, we keep it at, we kept it as a minus 14 to plus 14 or so degree Celsius. So this is the thermal regime that we applied during our frost heave and thaw settlement tests. And we had applied and tried 3 different cases. We compact our soil in 6 different layers. And I will mainly talk about case 1 and case 2 in this study, in this presentation, to ensure that we finish the presentation in timely manner. But with the case 1 and case 2, case 1 is with organosilane 1 treatment, and case 2 is with organosilane 2 treatment. And what we do, we mold the layer 2 and layer 3 in the case 1 and case 2. with different organosilanes. And the case 3A, we mold only layer 2, which is a 2-inch thick, 1-inch thick layer. And case 3B with organosilane 1, we have a molded layer and chemically sprayed layer. And in the case 3C and case 3D, we have only sprayed layers, one on top of layer 1 and one on top of layer 1 and layer 2. And why we did this chemical spraying layer, John will talk about the construction of the test sites. We applied, instead of doing molding, for instance, we applied chemically sprayed layer to, which is more practical, and we wanted to try that technology. And here are some of the how we prepare the samples, either it's molded with treatment or it was sprayed. And with the case 1 results, if you look at it for the Alaska Fairbanks soils, the open symbol shows the frost heave behavior and tow settlement behavior of the Alaska Fairbanks soil when it is untreated, and the other ones are showing the frost heave tow behavior of the Alaska Fairbanks with 0.1 and 1% organosilane 1 treatment. And as you can see, there is a significant reduction on the frost heave and tow settlement compared to when you treat your specimen with the organosilane. And this is kind of showing that, yes, you really stop blocking that water coming from the bottom of the soil and minimize that. By cutting that water, you minimize that frost heave tow settlement action. And similar behavior was observed with the Iowa Potawatomi County. Again, this technology has been working. Similar things were observed for North Carolina soil, and similar things were observed for New Hampshire, Hanover soil as well. So based on these free frost heave tow settlement test results, we really be able to, we show that, yes, in the lab scale, even 0.1% and 1% organosilane use is minimizing, and in many cases even completely, almost completely preventing frost heave and tow settlement actions. So here are the some of the cases, kind of summary. What are the percentage reduction in the maximum heave? It is almost 100% in some cases for some soils, but it is almost above 60%, almost 70% for case 1. And with case 2, the similar applications, except one with 10%, you see it's still 50% reduction, but if with 1%, you get to the 80 to almost 100% reductions in reduction in the heaves. And as this also shows, some of these percentage values and application methods may change depending on the soil type as well. Overall, it is very efficient with the majority of the soils, but the addition ratio may need to change a little bit and need to be taken into account when you apply these. And another thing that I wanted to show quickly is we created this hydraulic barrier, layers 2 and 3. As you can see, the treated ones here show how low the moisture content on the treated layers compared to untreated layers within the Alaska Fairbanks soils. And same thing happened with the case 2 with the North Carolina soil as well. The treated ones had lower, treated layers had lower, lower moisture content, indicating that this system, when you make the soil hydrophobic, it really prevents the moisture to be sucked in to the upper layers, so it minimizes the frost heave tow settlement damage. And here is a summary. The dark columns here shows the volume of water intake on the specimens that are untreated versus the treated ones. And as you can see, there is a significant difference between the amount of volume of water intake on the untreated specimens and treated specimens. So these lab laboratory test results really showed us that we really prevent moisture uptake with making the soil hydrophobic. There are, next two slides are a lot of words. I won't go read them one by one. Overall, the technology based on the laboratory test results, whether it is contact angle measurement, water droplet penetration test, or frosty tow element test. It minimizes the technology works. It minimizes the frosty tow settlement damage, and one results show that high concentration of organosilane doesn't necessarily may work. You really need to work with the soil that you have. And remolding seem to be working better, but spraying also do its job. And again, the moisture is being controlled with these treated layers, and so the technology, the laboratory test results that we got really encouraged us to apply this in the real field applications. And that's where really the current NRRA research project comes into question. And Dr. Daniels will talk about it, the construction stage, since he has been there during the first construction stage. Go ahead, John.
Yeah, so great. I mean, with all that lab-based work, it's one of these things where we've got sort of proof of concept at the laboratory scale. So let's try it in the field. I mean, that's why it's been so great working with Bora and his team, is we're focused on what can we learn from the field, and that's why NRRA is so vital, and this group is so vital. So the motivation hopefully is clear by now. That look, taking frost action as a challenge. How can we approach that? And so there's examples where you've got this excessive deformation, and we want to control that, and we want to prevent all the things which go with that, whether it's the rutting, the heaving, and excessive spring load restrictions that have to be put into play. So if you look, so the project that we have funded by NRRA had a number of objectives, and I won't read all of them to you. I just want to kind of get right to the interesting part of working in the field. And that was really our third objective, right? So after sort of this preliminary evaluation and characterization, let's go out and do something in the field. And so we were thrilled to be able to have a spot on the low volume loop. And so if you go on, you'll see the task there was really, okay, let's build these sections and monitor them at a place with a northern climate. So you see there, cell 2306 and 2305. Those are the two cells that we have. I think total is about 150 feet. I think each one is about 75 feet in length. So if you look there in plan view, just to orient yourself, you can see I-94 looking, to the left is west, to the right is east. And so you can see where our two cells are. And again, recall that this is intended to mitigate frost action. So do we have frost susceptible soils there? Check. Do we have the presence of water? Check. Do we have cold weather? Well, generally, check. Although you'll see it was a pretty warm winter this past year. So perfect location for these test cells. And so there was two phases of construction, although we have to confess we didn't intend to have two phases. Although, as folks on this call realize, this is sometimes what happens. So really phase one was the intervention, which was the construction and the treatment using a sprayed technique to ensure that we have water repellency. And then phase two was a consequence. I call it a bonus project. That's not something we signed up to have, but it was really challenges with the construction of the test sections. So if you go on, I'll walk you through some of the pictures there. So there you have, again, the idea is to prevent frost action, right? And so the idea is to excavate down to a depth and spray the chemical to prevent the capillary fringe and water from the groundwater table from coming up from below. Again, the assumption here is that you've got sufficient drainage to mitigate challenges from water coming from above. And we're really trying to prevent water from below. So we excavate down, this was to 4 feet. And then of course we have to put instrumentation in. So you see the wires on the left picture, and on the right, you see we got two hands in that hole, and sort of the hand on the left is touching what's called a pteros. I believe that's a 21. That's moisture potential. How tightly is water bound to the soil particles? Whereas the sort of the blockier white piece there, the hand on the right is touching a pteros 12. That's measuring things like moisture content. So we have both moisture content and moisture potential. Then we got to spray the chemical. Yeah, so you see there, we've got a manual in particular putting in the product, mixing it with water, and then that gets sprayed over our surfaces. So we have a treated section and an untreated section. We're getting ready to spray the deepest layer, which at this point was on the order of 3.5 feet. So we've excavated 3.5 feet down. And you can see that we're spraying the chemical according to the dosage and rate that we believe is going to make it water repellent. So I think the next slide has a video of what that looks like of the actual spray application. And really, it's much like you would think. It's somewhat analogous to a tack coat. Um, and so there are obviously challenges if the wind is blowing, and there's going to be some unevenness with regard to the treatment, right? You can see localized ponding in some places. So a question that often comes up is, well, how thick is it? Well, it's on the order of at least millimeters, but it could be centimeters, and it's going to be a variable thickness. So that's how we spray it. And we did that for this site 3 different depths. So that's after the spray. And again, you're looking at the treated section. So what happens is you spray it, and then you put your next layer of soil on, 6 inches of lift, and compact. And so that's yep, you can move on to the next slide to kind of get a better view of this, of the construction site. So again, and further out is where the treated section in, closer to the big pile of earth, closer to us, is the untreated section, and both are instrumented. And so if you go on to the next slide, you'll see what we have in terms of, okay, we've treated 1 layer. Now let's bring on the next layer of soil, compact it, and then spray that as well. So what we've done for this particular site is we've sprayed 3 layers. And the idea is to have a little bit of redundancy associated with that. So again, we've already treated a layer, we've added our soil, we've compacted our soil, and then we go on and treat again. So this is the construction process. So it's relatively quick. This can be done 2 different ways. This was the spray application method. You can also use the organosilane as the molding moisture content. After we've sprayed our 3 layers, we finish up the pavement system. And so here you see, I believe that's our base course. And after our base course is applied, I think the next slide will show that we had our wearing surface put over there. And so here we're pretty excited because we've done our intervention. We've treated it as designed. We've got our instrumentation in. We've got wires connected to a box you see there in the upper left. We got this done before November of 2023. It's Minnesota. We're looking forward to a very cold winter. And well, we didn't quite get a very cold winter. And so if you look here, this is a plot of soil temperature, and you see it as a function of time. And you see we got our instrumentation in. And if you notice on if you can see the numbers up top, so the blue is 0.6 feet, the pink is 2.3 feet. But notice it's really only not even a full foot that we got below, say, close to negative 10 degrees Celsius. Yeah. Briefly in January, but more or less not a lot of freezing conditions. And so if you look to the next slide, not a very robust test. Nevertheless, it was a modest test of what happens. And so you've got 2 plots there of settlement on the y-axis, and then we're looking at, so we have a shape array, and this is a device that enables us to look at deflection across the pavement structure. And so for our control, you notice it's a little erratic, but we actually have a little bit of the control, a little heave, whereas the treated, we actually have a little bit of settlement. So they are displaying opposite reaction. I see we have a question there from Joel, and we'll come back to that. So anyhow, so that's really the extent of what we've observed. We did not have a full test of frost action this past winter. It just wasn't cold enough. And so we're at a position where we're interested in fully testing the section. But prior to fully testing the section, you have to design and build the pavement structure to withstand normal loading. And that was a problem for a variety of reasons. And so there was premature failure. And I think, Bora, this is maybe where you're going to take over and talk about how, we had a design, but it really wasn't built to the design. And it doesn't have anything to do with the intervention. It's more that the section wasn't built as desired. But maybe I'll leave that over to you, Bora, as well as maybe handling, I don't know, was it Joe or Joel's question that came up quickly?
Yep, thank you, John. We built, just like John mentioned, we built the test sites thanks to, again, mnroad and Minnesota DOT for their help on this. And it is built in November 2023, and mid-April, it starts failing, especially the control section. We start seeing significant distresses. We will touch bases based on our forensic analysis, what might be the problem during that occurred. Not really because of the engineered water repellency technology. To be honest, the control failed significantly, but overall we start seeing some distresses on the treated sections too. It is not really nothing to do with even the materials itself. The overall design, the material, especially for base and the asphalt thicknesses that were used that we used is not thick enough, and also the material, the base layer that we put seemed to have a more fines content than it was, and it was RCA based material, so drench has become an issue. And also there was an issue on the, it's very close to the pond around there, and one thing that we think the moisture migration from that pond might also cause moisture piling up within these test sections and cause these premature failures. These are some of the major distresses that were observed on the test sites starting in mid-April. And I don't know if Jacob, I think I saw Jacob's name. Jacob, feel free to chip in if we say anything wrong, but I think Manuel and Wasi feel free to chip in too here. So go ahead. Is somebody saying something?
Yeah, no, I think the main issue was the pavement was not paved at the thicknesses that it was designed. I think we had some issues with the contractor not being able to place the material well and not being able to pave at the thickness that was designed.
Yep. Thanks a lot, Jacob. Again, thanks a lot for helping with reconstructing this test site. So here is a video actually John during initial construction picked that kind of shows even during that construction section, you can see water is coming from the road. That's how much amount of water that we had on this test sites, and this was perfect site for applying this technology. But to Jacob's point, especially the asphalt layer thickness were thinner than what was originally designed because of, I think it was end of construction season and contractors also rushed it a little bit, so we end up having some of these premature failures. But thanks to again Minnesota DOT and mnroad crew, we really appreciate their help. We had a chance to do a good amount of forensic analysis. They cut strips for us. They cut large portion of these large areas of these boxes for us, cuts for us, and then we were able to run dynamic comb penetration tests and lightweight deflectometer tests, and we were able to do many different coring points. We did asphalt corings as well to determine the thicknesses of each of these asphalt layers. Here are some of the pictures, and here are some of the pictures of cuts on treated cells, and we have bigger cuts for the control cells because it had major failures on the payment systems. Sorry, we had much bigger failures on the control cells, and here are some of the pictures of these cuts, and we run the tests on them and also collect quite a bit material to understand what was their index properties and their permeabilities and all that, and we're still running some of these special permeability tests. And here are the solid points are the DCP test points that we have conducted throughout the test sections. And the base layer thickness were pretty much supposed to be we aimed at for it to be 6 inches. And in some cases that thickness also seemed to be varying a little bit throughout the test section. But again, the main problem was the thickness of the asphalt layer thickness, and we have conducted lightweight deflectometer test. And again, when we run the LWD test and compared it with the mean pave design requirements, it didn't satisfy the requirements. So, and you can see we had quite a bit issues, especially in the control section for not being able to achieve the appropriate stiffness levels throughout both cells, but also particularly in the little bit lower stiffness values with the control cells. And here is a graph that kind of shows to Jacob's point, the asphalt thickness was fairly low, especially on the control cell. We had some of those in the treated cells too. So the thickness of the asphalt had had a big role on this premature failure. And then we had quite a bit back and forth with the tab members and with the mnroad with the tab members for this project and mnroad personnel, and we come up with a redesign, the agreed the design that we had. We cut the 2 inches of extra subgrade layer and put 6 inches very permeable DSP material, and on top of that we put thicker 6-inch asphalt layer, and also shoulder material seemed to be very low permeability. So we kind of also this on the original design we wanted to change and make that shoulder open graded and have its thickness to 1.5 feet. Then on top of then, of course, with the construction, some of the things didn't play as expected, but we did thanks to mnroad personnel again, did a very good job. We cut the clay subgrade and put the large stone aggregate, 6-inch large stone aggregate, and on top of that 2-inch DSP and 6.25 on average inch asphalt layer thicknesses, asphalt layer on our test sections. Here are some of the pictures. Again, it was milled to be reconstructed, and base and subgrade removal. Again, we moved 2 inches of subgrade to ensure that we have that 1 foot to play with the put on all the new base material and thicker asphalt sample there. And there's a proof roll on the shoulder. Instead of density test, we use the proof roll to ensure that we have somewhat satisfying subgrade compaction. Then this is a picture that shows the large stone spreading to improve the soft clay stiffness, because with the proof roll we kind of see the subgrade is too wet and still not at the levels that we wanted in terms of density, but we put large stone aggregates to kind of stabilize that layer. And here we did again some LWD tests after 12 hours after putting that large stone, laying that on, and the control section still seemed lower, a little bit lower stiffness, but it was manageable. And similar thing, we are done with the shoulder work. We put the we put a geotextile there on the shoulders to help out with to minimize some migration of subgrade soils on the surface and help with the drainage a little bit too. And here are some of those pictures. And then since this was an opportunity, we wanted to put some additional sensors. John, you want to mention a little bit about this?
Yeah, and within a few minutes, I'll tie it together with the questions from Fu Sheng and Joe Voles. And so, look, we didn't intend to have this extra opportunity, but we did. So the idea is to put some more moisture sensors in there. In part, Joe, thank you for your question. First up, we did not intentionally prevent the movement of water from the treated to control section. Now, it's sort of like any kind of test section, you have sort of boundary conditions. Our instrumentation is in the middle of each section, and so our hope is that as you get further away, in our case, we tried to instrument the middle of the sections, that perhaps the boundary conditions aren't influencing things as much. That's the hope. but we put in additional moisture sensors adjacent to it, and we're trying to capture additional groundwater data so that we can understand this movement of water horizontally. Because we did have an issue with, we have two sandwiches basically. Yes, if you go to that next slide, for example, Bora, you'll see the treated section has three layers, and if you look on the right there is this notion that water filled up artificially through our instrumentation and penetrated in between the layers. But we're trying to unpack what really is happening to water. Again, what are we trying to do? We're trying to prevent it from below. So like the question from Fu Sheng about, will installing subdrains mitigate frost heave further? Well, I suppose it could mitigate frost action in the sense that, perhaps you're limiting the amount of water that's resident in the subsurface. If that's happening for both the control and the treated section. And fundamentally, the goal is to prevent water from rising from below. So to the extent that that's happening, it should affect both the treated and the control. And really, we are optimistic with a colder winter, we'll be able to see, how the treated section works. But it's a great question that to the extent that you control drainage, you're managing moisture appropriately. So I think that's it for the sensors. Go ahead, Bor, if you want to finish us out.
Yep. So the next 5 slides just really by a lot of pictures that we put this 2 inches drainable stable base material after we install the sensors, and of course it's leveling and compaction done, and then the 6 1/4 HMA are being put, and it is put in the 2 lift off 3 inches HMA and 1/4 inch thin layer on the inner lane. In total, it was, I think, Cat wanted to try that specific treatment, 1/4 inch thin layer treatment on the inner lane. And this is how the test section looked like after second lift. And right after construction and putting that 1/4 thin layer on the inner lane here, this is how the test sections looked like. And as a continuing effort, we keep collecting the soil temperature frost line, and thanks to mnroad personnel and mnroad crew, they will keep collecting FWD data and share it with us, so we will analyze that. So we're collecting soil temperature, soil moisture, suction data, as well as the FWD data, and we will do LiDAR analysis on these test sections before winter hits as well. And then, as part of the study, maybe hopefully next year or spring 2026, we will maybe have another of these research pays of webinars to talk about the modeling of these behaviors. And as part of this research project, we will do modeling. So that's pretty much what we had prepared today, and I think John responded some of the questions.
There was another question there from Charles about how thick was the large stone base, the 12 inches of drainable stone base, and it was partially daylighted, but I don't know if you want to add to that, Bora, the question from Charles Kremer.
For the 2-inch drainable base?
Yeah, so the question is, how thick was the large stone stabilizing layer, and do you think that will act as a permeable layer, and does it have a water outlet?
We did it daylighted base, Charles, and it was a 2-inch drainable stable base, and underneath we have close to 4-inch large stone sub base. 2-inch is not that thick enough, but we have 4-inch large stone sub base, and we try to make them daylighted bases. We didn't have any outlets. We think that it will work. It is a little bit unconventional design because of the challenges on the material collection and all that. We think it will work, but hopefully next year the research pays off. I don't have to eat these words, so we think it will work, even though it's 2 inches. It's really very good drainable material, and we have 4 inches almost large stone sub base underneath.
And again, really thankful, all of mnroad, all of Minnesota DOT, but especially Jacob Calvert. This was so much. We tried to do so much work in a short amount of time. This was really not intended. And in fact, NRRA makes a point that says, look, don't come to us with a project and expect us to build it right away. And that's exactly what we did. We expect them to build it right away. It was unrealistic. They delivered. and worked mightily with the contractor, notwithstanding, the contractor was unable to get the pavement thickness, but just making a broader comment about research. Anytime you're an experimentalist, anytime you're doing field-based research, you're going to have all sorts of things which are imperfect. But having a team that can walk with you and troubleshoot real time is just valuable, and that's why I really do think that this is a premier facility that really benefits the entire country.
Yep. Any other questions, or are we good? Thanks a lot again, all, for funding this project and attending to the webinar.
Well, great. Thank you. Yeah, it appears that all the questions have been asked and answered. So we will thank our presenters once again and wish you all a great rest of your Tuesday.
Thank you all.
Thank you, Bora and John.
Thank you. Thank
Thanks.
everyone.
Thanks.